Hello, Chem 201. We are having our first official lecture right now. This will cover chapter 1 in our book, right? This is the book that we're going to do, Introduction to Organic Chemistry by Brown and Poon. So this is the text we're going to use, and the material that we're going to discuss right now is going to be part 1 of the lecture for chapter 1 in Chem 201 at Harper College. So let me share my screen and let's get to it. Now, again, this is going to be a review. This is a review of many topics that are critical to organic chemistry that you should have learned in your prerequisite class. I do have individual lectures on each particular topic that probably goes into a little more depth than what we're going to do in this lecture. So make sure you check out the folder that is entitled Review of General Chemistry in the module for week 1, because that will give you some reference materials if there is something that you feel that you don't know after we discuss all of this material in chapter 1 and you want to get a little bit more depth in terms of a lecture. So make sure that you are aware that those are available. So I'm going to turn myself off and then we're going to go ahead and start lecture. In chapter 1, again, these topics are going to be a review of general chemistry topics that are important for organic chemistry. So we're going to be looking at covalent bonding and shapes of molecules. The first thing I want to talk about is what distinguishes organic chemistry from inorganic chemistry. And I think we all know that carbon is one of these distinguishing features. Organic compounds are basically carbon compounds, and they encompass different industries such as food, clothes, pharmaceuticals, plastics. Organic compounds are everywhere. And if any of you guys are going into health fields and you have to take a biochemistry class, you're going to realize that all of the biomolecules that your body uses to function, such as proteins and nucleic acids and carbohydrates and lipids, all of those things are considered to be organic compounds. So why carbon? Carbon is a small atom. It forms 4 bonds because it has 4 valence electrons. Those bonds it forms can be single, double, or triple bonds. It has an intermediate range in terms of electronegativity. Remember, the Pauling scale goes from 0 to 4. So the electronegativity of carbon is about 2.5. It forms strong covalent bonds with itself, with carbon, with hydrogen, with oxygen, nitrogen, sulfur, the halogens, and some metals. So the sheer diversity of bonding that carbon allows is one reason why this is such an important atom and element in nature and in organic chemistry. What you should be bringing to this class is an idea of atomic theory, how electrons are populated in atoms or in orbitals around the nuclei of atoms. You should be able to draw electron configurations, and you should be fairly comfortable with ionic and covalent bonding models. Just to review, a covalent bond forms when electron pairs are shared between 2 atoms whose difference in electronegativity is 1.9 or less. So if I have 2 hydrogen atoms, each one has 1 electron, hydrogen, to fill its valence shell, wants a duet because it wants to be like helium and want to be like a noble gas. That's one of the rules of bonding. For hydrogen, because it's a row one element, a period one element, one additional electron is going to complete the valence shell, which is the driving force for this reaction to occur. This negative sign means this is very exothermic, which means this formation of this bond is actually very favorable. Remember, there is a property of elements that is called electronegativity, and this is the measure of the force of an atom's attraction for the electrons it shares in a chemical bond with another atom. We can use the periodic table in order to assess electronegativity. This is going to have a periodic trend where it increases from left to right, and it increases from bottom to top. The most electronegative atom is fluorine with a 4.0 on our Pauling scale. So this is the most electronegative atom. Down here is going to be the least electronegative atom. So even if I don't have a chart of electronegativity values, what I do know is as I go away from fluorine, my electronegativity is decreasing. As I go towards fluorine, my electronegativity is increasing. This is an online class, so you should definitely have a chart like this available for you to consult whenever you get confused about if something is going to be a polar bond or a nonpolar bond. This is one that is pretty easy to use. It's color-coded so that you can sort of see trends based on the colors. Notice that the most electronegative atoms are up and sort of make an upside down inverted L up here. And nitrogen, oxygen, and fluorine are going to be the electronegative atoms that we really consider in organic chemistry. The halogens as well, but this whole area of nonmetals here is going to be what we're going to focus on in terms of organic chemistry. And mostly we focus on covalent bonding. So remember, I can classify the chemical bond that forms between two atoms by looking at the difference in electronegativity. A lot of times I'll write that as delta En. If it is less than 0.5, so if I take the electronegativity value of the atom and then subtract the electronegativity value of the second atom in the bond, if that difference is less than 0.5, it's considered nonpolar covalent. If it's between 0.5 to 1.5, or I mean 1.9, it's going to be polar covalent. And if it's greater than 1.9, it's going to be ionic. Remember, typically, two nonmetals or a nonmetal and a metalloid are going to form covalent. And then a metal and a nonmetal will form ionic bonds. We're going to see that there are some cases such as carbon magnesium and carbon lithium where these are metals plus nonmetal, but they're actually considered to be polar organic or polar covalent. Because if you look at the difference in electronegativity, they sort of fall in this 0.5 to 1.9 range. And that gives it some interesting properties. But right now, just focus on this, be able to know if you look at two atoms engaged in a chemical bond, what type of bond that it's going to form. Is it going to be nonpolar covalent, polar covalent, or ionic? So in a polar covalent bond, the more electronegative, so the more electronegative atom has a partial negative charge. And a lot of times you'll see this as a partial negative. That's like this little delta. The less electronegative atom is going to have, so if I have, put this in a different color, the less electronegative atom is going to have a partial positive charge, which is a partial plus sign. In an electron density model, this area here has got high electron density, this red, and then this blue area has got low electron density. So the electron density is all shifting this way, which means this is partially negative because it has a buildup of negatively charged electron density, and then this is partially positive. It's not a full transfer, so I can't call this an ionic bond, but because the electrons are shifting towards the more electronegative atom, it is a polar covalent bond because I do get a charge distribution within the bond and then the molecule. Now let's look at Lewis structures. This is another core feature from general chemistry that you need to know. Remember that in terms of Lewis structures, the Lewis theory of bonding deals with electrons that are in the valence shell. So this is the outermost electron shell of an atom. Valence electrons are used in forming chemical bonds. So the valence electrons are those electrons found in that outermost shell as I'm filling electrons in my orbitals. And I know that these electrons are the electrons that are actually involved in forming chemical bonds. Now, the Lewis structure, or the Lewis dot structure, is where I have a symbol of an atom that includes representing the valence shell electrons by dots, right? So the symbol of the atom itself represents the nucleus and all the inner shell electrons. The dots are going to represent electrons in the valence shell of the atom. So for oxygen, I have 6 electrons in the valence shell. So I would have 1, 2, 3, 4, 5, 6. And this would be the Lewis dot structure for oxygen atom as taken off of the periodic table. Now what's interesting is that valence shell configurations are similar as I go down a group. So notice in group 1A, I always have 1 valence electron. In group 2A, I always have 2 valence electrons, and so on and so forth. So the shell that's being filled is going to be different as I go down a column in a group, as I go from period 1 to period 2 to period 3, etc. But the number and type of valence shell electrons is going to be the same. So for anything in 1A, I have a single valence electron in an s orbital. For anything in 2A, I have 2 valence shell electrons in an s orbital. As I go from 3 till 8, I start filling those 3 p orbitals in any given shell. And you can tell that I'm going from group 1A all the way to group 8A. These are my noble gases. And the group number, as long as I'm using these A's, is indicative of the number of valence shells that are available for bonding. Now remember, if I go down to third group elements, I could have situations where I have more than 8 electrons, This is called an expanded octet. And this is due to the fact that when I get into period 3 and 4 and 5 and so on, I have d orbitals available, which allow for an expanded covalent bonding opportunity for elements that have those orbitals available to them. In organic, we spend a lot of time considering Lewis structures. We do not just look at molecular formulas anymore. We want to see which atoms are bonded to which other atoms. And we also want to see if those bonds are single, double, or triple bonds, and if I have unpaired or paired lone pair electrons involved in the structure. If you recall, the octet rule was a very large, important rule, which says that atoms tend to gain, lose, or share electrons. This would be for ionic bonding models, and this is for the covalent bonding model. And the number of electrons that are gained, lost, or will be shared allows the atom in question to achieve a noble gas electron configuration, or to have 8 valence shell electrons, which means my S shell and my P shell is going to be filled. So again, if I transfer, which means I gain or lose electrons to form positively charged cations or negatively charged anions, that is what I'm considering ionic bonding. And then covalent bonding would be where my atoms actually share electrons. And if I do have a difference in electronegativity, I can have an internal charge distribution as electrons shift from the less electronegative atom to the more electronegative atom to form a partial negative or a partial positive within the bond or the molecule. So you need to know how to draw Lewis structures. You're going to draw the individual atoms using dots to represent the valence electrons. And then you're simply going to put the atoms together so they share pairs of electrons to make complete octets. For example, if I look at nitrogen, I have 5 valence electrons because this is in group 5A. My hydrogen is in group 1A, so it has 1 valence electrons. Notice that I need to gain 3 electrons to make an octet, and each one of these needs to gain 1 to make that duet and fill the hydrogen outer shell. These common bonding patterns, I refer to those in the individual lecture that is in the review folder. And basically, for nitrogen, I want to form 3 bonds, and I will have 1 lone pair. That is my common bonding pattern for nitrogen. So if I stack these hydrogens around the nitrogen, and then I literally just connect the dots, what I get is here, and notice I have 3 bonds and 1 lone pair. My nitrogen has an octet, and then each of my hydrogens has a duet. I do double count those electrons. Everybody has a filled outer shell. Everybody's happy. So you do have to be familiar with these common bonding patterns that I discuss in a different chapter or in a different lecture. So my Lewis structures are going to be things like this guy with water, remember oxygen, has 6 valence electrons and it has the 2 hydrogens. So if I put them across, I'm just gonna connect the dots, hydrogen and chlorine. I put them together, I'm gonna connect the dots. So you get the idea. I look at the valence electrons available for each of the atoms. If I'm charged, if I'm a negative charge, I can add electrons to my Lewis dot structure. If I'm a positive charge, I count up all the electrons and then I would take one away. Remember, if I can't fulfill an octet in any other way, I can form double and triple bonds. So for example, with acetylene, I have 2 carbon atoms and then I have 4 hydrogen atoms. When I form those double bonds, or when I form those single bonds, I still have 2 electrons left. Well, those are going to go in to form this double bond in order to give carbon an octet on either side. The same thing can happen when I look at oxygens. If I look at this guy, if I have formaldehyde, acetylene happens because I have to share 6 electrons between those carbons in order to fulfill the octet. You want to be careful when you have multiple central atoms because it's easy to sort of go awry when you have more than one atom. I'm going to show you that in organic chemistry, we actually write things in a way that helps set up the connectivity of the atoms. So for carbonic acid, because it's an acid, the hydrogen is in the front, and that's just because it's an acid. But this is implying that the oxygens are attached to carbon, that are attached to carbon because of they're followed to the right of carbon. I'll talk about that a little bit more in depth later. So in order to draw Lewis structures, you're going to draw the individual atoms using dots. You are going to put the atoms together so they share pairs of electrons to make complete octets. Basically, I'm connecting the dots. And I must use these common bonding patterns as a guide. So if you haven't already checked out my individual lecture in the review folder on Lewis dot structures and how to draw them, please do that, because what you're going to do is be able to look at what those common bonding patterns are. That is pretty critical for being able to easily draw these different types of structures. Now, this is what I mean by looking at a structure and sort of reading it in organic. This is saying those hydrogens, because they're right to the right of that carbon, are attached to the carbon. So that, and then I have another carbon where the hydrogen and the oxygen are attached to that carbon. I'm actually reading from left to right. So what I have is carbon, carbon, and then oxygen, and then I have a hydrogen in that regard. So I'm going to put my 3 hydrogens around here, and then I'm going to notice that in order to give everyone an octet, I end up with this structure where I have a double bond between the carbon and the oxygen. If you do this using the connect the dots, you can also do it that way. And then I would have hydrogen, 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 hydrogen. If I connect the dots, what I'm going to notice is I have these 2. I put those here in order to form this double bond. Notice on this guy, I'm also going to read in the left to right direction. So these hydrogens are on this carbon, these hydrogens are on the nitrogen, and the carbon is attached to the nitrogen. So I have carbon, nitrogen, right? And I have H, H, H. I know that nitrogen forms 3 bonds and has 1 lone pair. So this is the Lewis dot structure for this compound. So again, it comes back to those common bonding patterns. You're going to be able to do that. I'll do it up here if I look at that one and I go connect the dots. Right? I'm going to have this guy here, this guy here, this guy here, this guy here. I have another hydrogen, another hydrogen. I do this, and I end up with the structure that I have down here. So if you have to sit there and do it individually for a little while where you're connecting, at some point you're just going to be able to look at this structure or look at this structure and just draw the Lewis structure. It might not be for a while. There is a huge learning curve in the first couple of chapters of organic chemistry because organic is so vastly different from general chemistry. So if you're struggling, that is totally acceptable, and it's actually to be expected because of the nature of the difference between organic and inorganic. I am here to help you. So what you need to do anytime that you're struggling is make sure that you actually call me, get in touch with me, and let me know how I can help you. Now, we also want to look at formal charges in Lewis dot structures. Remember, an anion is a negatively charged atom. A cation is a positively charged atom. In Lewis structures, in organic chemistry, many of the times we're going to have something called a formal charge within a Lewis dot structure. Now, anions are atoms and molecules that are sharing electrons. So these are covalently bonded molecules, are typically neutral, but they can also be anionic or cationic. So we have to be able to determine the formal charge for an atom in a given molecule. To do this, we look at the number of valence electrons that atom is supposed to have based on the bonding pattern and the position in the periodic table. And then we're going to compare that number to the number of the valence electrons that atom needs to be neutral. Okay, so actually I stated that backwards. I sincerely apologize. I'm going to take the number of the valence electron that it owns based on the structure in the Lewis dot structure, and I'm going to compare it to the number of valence electrons from the periodic table. Again, I have a mini lecture on this topic if you need to have more, more in-depth talk about this, but let's look at this. Let's look at these atoms. If I have, this is actually going to be CH3O minus. So what I have is I have 4 valence electrons from carbon. I have 3 electrons from the hydrogen. I have 6 electrons from oxygen. And I have 1 electrons because I have a negative charge. So that gives me a total of 4, 7, 8, 14 electrons. So I have to account for 14 electrons. How do I do this? Well, this guy has 7 electrons instead of 6, all right? Because if I do that, I'm going to connect, 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 connect. This still has an octet. This is going to have an octet. This has a duet. This has a duet. This has a duet. Everybody has their outer shell filled. So this is a valid Lewis structure. So where is this charge? Let's look. I'm going to look at oxygen. I had to close the window in order to get that lawnmower out of there. So this oxygen is supposed to have 6 electrons based on the periodic table if it's neutral, right? But it has 1, 2, 3, 4, 5, 6. I count half the bonding. It actually has 7 electrons from this LDS structure, the Lewis dot structure. So it has 1 electron extra, which is a negative charge. This oxygen is negatively charged, so I can put a minus there. Carbon, does that have a charge? It's supposed to have 4 electrons. I have 1, half the bonding, 2, 3, 4. That's actual 0 charge, right? So the negative charge is actually on the oxygen. So this is what you're going to do. This here is my normal bonding patterns. This is where I really don't have a charge. Remember, boron is an exception to the octet rule. It only likes to have 6 electrons. Carbon forms 4 bonds, 0 lone pair, and it can have single, double, and triple bonds. Nitrogen likes to form 3 bonds, 1 lone pair, and then oxygen likes to form 2 bonds with 2 lone pair. Nitrogen can be single, double, and triple bonds. Oxygen can be single and double. So when you look at that, those are my common normal bonding patterns, and that generally gives my central atom a formal charge of 0. Here, I have fewer electrons. Here, I have more electrons. And notice that all of these structures, more or less, will follow the octet rule. These won't. These will be, some of them do, some of them don't. For example, this carbon only has 6 electrons, the absence of that valence electron, right? So let's look at that here. And that carbon is supposed to have 4 electrons. If I look at half the bonding from the LDS, I only have 3 electrons, so that is a positive charge. Nitrogen is supposed to have 5 electrons. If I look at half the bonding, it has 4 electrons, so that's a positive charge. So I can assess the charge on each one of these molecules, or each one of these atoms, and that's how I get this +1 or this -1. I could have +2 and -2 as well. Let's look at this guy. Carbon is supposed to have 4 electrons. Here I have the lone pair, 1, 2, half the bonding, 3, 4, 5. It has 5 electrons, so it's a -1. That's how I get this charge in there. So make sure that you can look at a structure. You can use Lewis dot structures. Like I said, up here, this oxygen has an octet. It fulfills the octet rule. It's got the right number of electrons. It just happens to be charged because the way the electrons are distributed within the molecule, carbon's supposed to have 6 electrons to be neutral, but it actually has 7. I have that extra electron, which is giving me that negative charge. So this slide here, showing these different common bonding patterns that give me neutral compounds and also give me charged compounds of +1 and -1. You should be able to see why all of these different structures for these different atoms are +1, 0, or -1. You should be able to look at a Lewis structure and determine what the formal charges are in that Lewis structure. That's going to be a critical skill as we go forward. If you have any questions, make sure you let me know. Here's an example. We've done a couple of those. Let's look at maybe this guy and this guy. And we'll start with those. So again, I'm reading left to right. So these hydrogens are attached to the carbon. These hydrogens are attached to the nitrogen. Notice I have a positive charge. So carbon has 4 electrons. I have 3 hydrogens, that gives me 3 electrons. I have a nitrogen, which gives me 5 electrons. I have 3 hydrogens, again, that gives me 3 electrons. So I have 7, 8, I have 15 electrons. But I take away because I'm positive. So I have 14 electrons to work with. I know my carbon is attached to the nitrogen, and I know those hydrogens are attached to the carbon. I also know that I have 3 other hydrogens attached to that nitrogen. So where is my positive charge? Carbon, 4 electrons, half the bonding. 1, 2, 3, 4. That's a 0 charge here. Nitrogen, 5 electrons. I don't have a lone pair, so half the bonding gives me 1, 2, 3, 4 electrons. I have 1 too few. My positive charge is on nitrogen. So this is how I'm going to look at these molecules. Let's look at CH3OH2 plus, right? That's I. Again, this is here, this is here. I'm reading left to right. I have 4 electrons from carbon. I have 3 hydrogens, which gives me another 3 electrons. I have 1 oxygen, which gives me 6 electrons. I have 2 hydrogens, which gives me 2 electrons. 7, 8, 9, 15 electrons. I need -1 electron. Again, I have 4 electrons total to play with. So my carbon, I'm going to do this one, connect the dots. My oxygen, I'm going to now have hydrogen, hydrogen, hydrogen. Now here's the thing. I am going to go ahead and take away that electron because I wanted to remove an electron because of the charge. So now if I put my hydrogen there and my other hydrogen on the oxygen, when I connect the dots, what you're going to see is I have oxygen with 3 bonds and 1 lone pair. Well, that's not the normal bonding pattern. Carbon has 4 bonds. That's the normal bonding pattern. Oxygen is supposed to have 2 bonds and 2 lone pairs. What it has here is 3 bonds and 1 lone pair. So let's count the charge here. If I have 6 electrons where it's supposed to have, I take half the bonding. I have 1, 2, 3, 4, 5. I have 5 fewer electrons, or I have 1 fewer electron, so I have a positive charge. This positive charge is on the oxygen atom. And that's because I'm looking for things that don't fulfill or that don't follow the normal bonding patterns. So here, when oxygen has 3 bonds and 1 lone pair, it's positive. Here, when nitrogen has 4 bonds and 0 lone pairs, it's positive. So again, if I look at this chart, when I have 3 bonds and no lone pair, my nitrogens are going to be positive. When I have 3 bonds and 1 lone pair, my oxygens are going to be positive. So this chart is really, really handy, especially when you start looking at these sorts of types of charges that you're going to see all the time in organic. So go through the rest of these yourselves and then see if you can draw the Lewis structure. If you don't, give me a ring and I will help you figure out where to go. There's one more topic I want to discuss before we take a break, and that's resonance, right? Many times when I draw a Lewis dot structure, molecules and ions may be able to be best described by 2 or more. So if I draw one, that doesn't mean that's the only one that is acceptable according to the Lewis dot structure rules. There could be 2 or 3 or more. And anytime I have 2 or more Lewis dot structures that are describing the same molecular ion, and they're valid, and they follow all the rules, those would be called individual resonance structures. Those individual resonance structures are called contributing structures because the molecule in nature is going to look somewhere in between all of those structures. So I can actually show how I get from one resonance structure to another resonance structure by pushing double-headed arrows, which show my flow of electrons in this situation. So physically, in nature, the molecular ion is actually going to be a hybrid of all the various contributing structures. So there are going to be some assumptions that we make when we look at resonance structures. Atoms do not change positions. The connectivity of the atoms has to remain the same. What does change is the distribution of the electrons. So I can redistribute the bonds and the lone pairs. Lewis structures do not always explain properties of these molecules. Resonance theory can give me another explanation when I look at behaviors. It's another second layered approach that sort of explains some behaviors that I see in nature, which we'll be talking about a lot in organic. So let's look at the carbonate ion, right? This is CO3, 2-. So I had to have 4 electrons from the carbon, 3 times 6 electrons from the oxygen, and then 2 extra electrons from the -2 charge. So I have 18, 24 electrons total. To get this, what I notice is I have this structure, or this structure, or this structure. What are the differences? The difference is the positioning of the electrons. Notice I have different positioning of those double bonds and those lone pair. That's what I usually change when I go from one resonance structure to another. So here, if I show the shift of electrons, this lone pair is going into this bond. My curved arrows, which we're going to get really used to, always start from an area of high electron density and go to an area of lower electron density. So my curved arrows always originate from electrons, which are either unshared pairs or bonds. If I move those electrons, that carbon atom will have too many electrons if something doesn't move out. So this bond, right, each one of those bonds is 2 electrons. 2 electrons from that double bond is going to go onto the oxygen. So now I have, instead of 2 lone pair, I have the 3 lone pair, and then I have a double bond. That's the change. And I can go from this second, so I have 1, I have 2, I have 3 structures by doing the same things, right? If I actually take my lone pair and I follow it, if I push this in, I have to take lone pair out, and that gives me the double bond, and then now I have 3 lone pair around that oxygen. So again, you should be able to draw the carbonate ion or something like it, and then you should be able to shift electrons using the curved arrows in order to show how I get from one resonance structure to another. This takes practice. It takes a lot of practice. Practice with your homework. Look at those individual lectures where I did go into more detail in the other folder. But just recognize that I'm going to use these curved arrows all the time. And my arrows can either originate from bonds or lone pair. And I need to be able to track the flow of electrons when I go from one resonance structure to another in order to be successful in this course. So let's look a little bit more in depth in this curved arrow. This is a symbol that is used to show the redistribution of valence electrons. It's really useful in resonance. It's also going to be really, really, really useful in mechanisms, organic reaction mechanisms, right? When I use curved arrows, I can only do 2 types of electron redistribution. I can go from a bond to an adjacent atom, or from an atom to an adjacent bond. Electron pushing by the use of curved arrows is a necessary, essential survival skill in organic chemistry. You need to learn this pretty well. Again, the learning curve in the beginning of this class is staggering. You're not alone. If you're sitting there confused, that's okay. It does take a little while in order to get this down. I am here to help you. Do not panic. Reach out. We can schedule a Zoom session. We can go over, we're going to have Zoom problem solving sessions where we'll go over all of these different homework problems and other problems that will illustrate these different skills. The beginning of any organic class is very difficult because we're learning something in a completely different way from anything we've ever learned before. You don't have a lot of background knowledge in these areas. So when you draw a resonance structure, you have to follow these rules. Every contributing structure, so every resonance structure, has to have the same number of valence electrons. I can't add or subtract electrons from one resonance structure to another. If it's charged, I add or subtract the total number of electrons in that particular structure, and then that's the same number from resonance structure 1 to 2 to 3 to whatever. I have to obey the rules of covalent bonding. So I can have no more than 2 electrons in the shell of hydrogen, no more than 8 electrons in any second period. Third period and anything in the fourth, fifth, or sixth may have up to 12 electrons. Remember, that's an expanded octet, and that's because of the d orbitals. My resonance structures are only going to differ in the distribution of valence electrons. My connectivity has to be the same. I also have to have the same total number of paired and unpaired electrons from one resonance structure to another. Again, this does take practice. Examples of ions in a molecule that's best represented as resonance hybrids would be these that carbonate. Let's look at the acetate ion, right? So I have a negative charge there. So I'm going to have the hydrogen connected to the carbon, the oxygen's connected to the carbon. So I have carbon with 4 valence electrons. I'm going to put those 3 hydrogens next to it. I'm going to have another carbon with 4 valence electrons. I'm going to have 1 oxygen up here. I'm going to have 1 oxygen down here. And notice I'm going to have another electron. So I'm just going to throw it there, and I can rearrange it in a minute. Here's my connected dots, right? Well, look at that. I have this electron and this electron. That's going to go there to make a double bond. So what do I have at the bottom? I have H, C, H, H, C, double bond O with 2, and then I have this. My negative charge is on this oxygen because I have 6 electrons. I have 1, 2, 3, 4, 5, 6. Half the bonding is 7. That gives me the negative. Now notice I have lone pairs and a double bond. If I go ahead and redistribute those electrons, I could do this and then pull those out. I use my double-sided resonance arrow, and what I'm going to draw is the second resonance structure. Notice nothing has changed on this carbon. The position of the lone pairs and the double bond has changed. So these 2 are resonance structures. Okay, so try this problem on your own. We will come back to this. What you want to be able to do is recognize that this is neutral. So I have 2 times 5 plus 6. I have 16 electrons total, right? I have a connectivity of NNO, and I want to be able to draw the resonance structure and also look at those formal charges, right? So the first answer, how many valence electrons, would be 16. If I do draw that as N, right, I have 16 valence electrons. I have the connectivity NNO, right? So that's going to give me right? So I have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Just by taking these normal, the valence electron configuration, what I have is this to work with, right? These are all row 2 elements, so I can't have more than 8. So when I look at this, let's start playing with it. Well, let's take this here and this here, and I'm gonna do this. Okay, 2, 4, 6, 2, 4, 6, 8. Well, that's all fine, but I don't have enough electrons on that nitrogen. So what if I redistribute this? One of these comes in here along with this. This one is going to come on the outside. So what I'm going to have is nitrogen with 2 lone pair, a double bond here. Now, it's neutral. So the sum of the formal charges has to equal 0. So let's look at formal charges. I'm supposed to have 5. I have 1, 2, 3, 4, 5, 6. This is a negative charge. I have half the bonding. Here I'm supposed to have 5. I have 1, 2, 3, 4. This is going to be a positive. Here I have 6 electrons. 1, 2, 3, 4. Half the bonding is 6. That's 0. So here, plus and negative equals 0. So I can have this internal formal charge. That is not a problem here. Now, let's see if I can get another resonance structure by redistributing electrons. If I go this way, I could do this. And then what I'm going to get is nitrogen with 3 lone pairs. Like that. Does that work? Let's see. I'm going to look at formal charges here. I have 1, 2, 3, 4, 5, 6, 7. I should have 5 electrons. I actually have 7. So this is a negative 2. 1, 2, 3, 4. This is a plus 1. Oxygen's supposed to have 6. I have 1, 2, half the bonding. 3, 4, 5. It's supposed to have 6. It has 5. So this is a plus. My negative 2 plus a positive 2 is equal to 0. I have 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Every one of these has an octet, so that is okay. Is there another resonance structure? Well, let's look at it this way. If I go and I do this, I'm going to have nitrogen with 3 bonds to this nitrogen. And then I'm going to have 3 lone pairs on that oxygen. So nitrogen has 5, 1, 2, 3, 4, 5. That's 0. So that nitrogen has a 0 charge. 1, 2, 3, 4. This nitrogen has a plus charge. 1, 2, 3, 4, 5, 6, 7. Oxygen should have 6 electrons. It has 7. That has a negative charge. Plus and minus is equal to 0. So I actually have 3 different resonance structures for this particular molecule. I can do this one, I can do this one, and I can do this one. The connectivity is the same, but the distribution of the electrons is different. And I have different charges on different atoms. Remember, my best structure has fewer negative charges. So this has the most formal charges. This has a plus and a negative, right? So this only has a plus and a negative. This only has a plus and a negative. So this structure is the worst because it has the most formal structure or formal charges. And they're of higher magnitude. So I have a -2 and I have a plus and a plus. These two, this guy here and this guy here, which one is better? Well, here, my negative charge is on the more electronegative atom. So this is the best structure, and this is in between, because even though I have only two formal charges, my negative charge here is in the least electronegative atom, which is worse than the one on the bottom. So to summarize, this one is the best structure of the three, if you had to assess that. All right, we will stop here for this particular session. So hopefully this makes sense, and if it doesn't, go back and look at those other lectures that I actually put in the week 1 module, and I'll see you soon.